Okay, so new topic for today. We're going to talk about something called triple integrals. So we've talked, let me just remind you what we have done. Obviously, we started with a very brief conversation about single variable integrals, and here's a couple of applications that I gave you for single variable integrals. On the one hand, of course, everybody's sort of cornerstone default application in a single variable calc class is to think about area under the curve. All right. And as you'll recall, I've spent a fair amount of time, let's say, bringing into question whether that should be your primary point of view on single variable integrals. But anyway, I'll come back to that. The other application being this one of, for example, maybe you want to compute the mass of a rod thought of as one-dimensional. Of course, it's not actually one-dimensional. But if you think of mass per unit length, then effectively, for the purposes of the computation, as if it's one-dimensional. Okay. All right. So then the next thing we did is we talked about double integrals, and the nice thing about double integrals is they're a lot like single variable integrals. And note the analogous applications that you get. A double integral, in the same way that you can compute area under a curve with a single variable integral, double integral lets you compute the volume under a surface. In both cases, the graph of the function that is the integrand. Right, so strong analogy there. It's a kind of you might say this is a two-dimensional version of what we had previously seen in one-dimensional version. All right, this has a one-dimensional domain. This has a two-dimensional domain. Why is that erased? Oh my gosh, I opened the wrong file. Okay, so sorry for the disappearance of my notes. Here's what happened. I wrote these notes with my stylus, and I forgot they weren't written hard. So I've let me just back arrow through what I've done here. I think that should be it. Okay, all right. Sorry about that. Okay, so another way to think about double integrals, or another application, you might say, that you can apply double integrals to help you solve, is for computing, again, mass. Instead of mass of a one-dimensional thing, how about mass of a two-dimensional thing? By two-dimensional, what we mean is we're keeping track of how mass is distributed over an area. Right? Thinking of it as two-dimensional. So the units here are mass per unit area. Okay. All right. So, what's a triple integral? Well, we have different ways that we could try to motivate a triple integral. I mean, we could take the point of view of this sort of category of applications and ask, well, what's the next step in this analogy? Here I have a two-dimensional area over a one-dimensional domain. Here I have a three-dimensional volume over a two-dimensional domain. What's the next step? I don't know, right? I mean, I guess it would have to be a four-dimensional volume under a three-dimensional hypersurface inside of R4. That would be the graph of a function of three variables. We can't draw the picture. We can't visualize what that looks like. It's not a good way to think about a triple integral. On the other hand, in the mass category of applications, the analogy is fine. In fact, arguably the analogy is even easier than the previous steps. So in the same way that you can talk about mass of a one-dimensional rod or a two-dimensional region, let's just talk about mass of a three-dimensional solid. And what I mean by even easier than the previous versions, here, trying to think of a three-dimensional solid and how to compute the mass of it, given how mass is distributed, I think of density as mass per unit volume, which is how we're kind of more accustomed to thinking of density anyway. Right? That's what they teach you in ninth grade physical science class or whatever. So it really is a very natural thing to think about. So this is what I would like to propose should be your first sort of intuition, your primary way to think about triple integrals. What is that triple integral? What image should you have in your mind when you think triple integral? This picture, right? Now, a common mistake, I think, is for students to think about single variable integrals like that, and double integrals like this, and then triple integrals like that. And you see the problem, right? I mean, the problem is that these are completely unfair comparisons. I mean, these are different contexts. Here we're looking at graphs. Here we're not looking at a graph. There are really different ways to think about integrals. So for the purposes of thinking about triple integrals, you have to think about triple integrals from this point of view, and therefore to be able to kind of motivate, the comparisons, you really have to think about single variable integrals and double integrals in these ways. So I'm a big fan, and I know, by the way, I know how deeply embedded in your minds this point of view on single variable integrals is. Right? And it has its purposes, right? And we made nice use of this point of view on double integrals, right? Full confession. Okay. So that's nice. I'm not saying throw that away completely. I'm just saying make sure that you're sufficiently flexible. Make sure that this is only one way that you have in your mind of thinking about single double integrals. And you should make sure that you are very, very good at thinking about these 2 points of view here on single integrals and double integrals. Because this is your only choice, really, for how to think about triple integrals. Okay. Right. So moving along, here's our definition. Definition of a triple integral. It's a Riemann sum. You'll notice that this Riemann sum formula is, really, really similar to what we wrote down for double integrals. Same kind of thing. In fact, you just based only on the symbols, you might have guessed that it would be something like this. I'm going to zoom one more notch here. Notice that instead of a summation over, let me zoom, sorry. Instead of a summation over two variables, two indices, now it's a summation over three indices. Not just I and j, it's I, j, and k. There are three coordinates describing where you are in the domain. Right? We're multiplying not by length, not by area, but by volume. And what we're talking about in those in that algebra is what we have entered in this picture right here. Not a one-dimensional interval, not a two-dimensional region, but if you have a three-dimensional box that is your domain, such as this one, right? Three-dimensional solid. You can talk about slicing or dicing or mincing, I don't know, whatever the right cooking terminology is. Breaking this domain up into little pieces, little sub-boxes. And for whatever reason, depending on your application, maybe you'd want to multiply the size of this box, volume of this box, times the value of some function evaluated in that location. Now, again, what is this function you want to multiply it by? Well, it depends on what you're computing. If you want to compute the amount of mass inside of the box, then you would multiply density times that volume. Right? If you want to compute the number of, let's say there's mosquitoes flying around there, you want to compute the grand total number of mosquitoes, well, you would multiply mosquito population density, right? Mosquitoes per unit volume, which you multiply by volume to get the total number of mosquitoes. Right? Or maybe there's maybe this is a fish tank and there's a concentration of some sort of pollutant inside of your fish tank, and you want to compute what's the grand total quantity of pollutant inside the fish tank. Well, then it'd be concentration, right? So pollutant per unit volume that you would multiply by volume. Okay. So lots of different applications to which you might apply this algebraic construction here. Okay. All right. Okay, so a couple of examples. I've kind of already talked through these examples, so I'll be quick here. But if you want to compute the mass inside of a box, mass is an accumulating quantity. Total mass is the sum of a bunch of little slices of mass that you get when you break up your domain. On each little box, mass is density times volume. More to the point, mass is volume times some function. Right? Size of the box times the value of some function. In this case, appropriate to the application of mass, that function is density. Okay, again, yes, we can rewrite that Riemann sum we now have this new notation further higher up on the page that we're going to refer to this algebraic construction by this notation here of a triple integral. Right, and I suppose that instead of developing to a full Riemann sum and then using Riemann sum shorthand, you could, and this is very common, use the integral shorthand as you develop the Riemann sum. And it is very convenient and this is very common. It's totally fine. I encourage this. But keep in mind when you write stuff down like this, triple integral dm. Right? Keep in mind you realize this is just a shorthand for a Riemann sum. Right? There is no m axis, right? And yeah. Okay. All right. Morally equivalent example. Suppose you know the population density of number of bacteria per unit volume inside of an aquarium. Well, the total population of bacteria is the sum of the populations in each little little region that you break it up into. Population is cumulative. And on each little piece, population is population density times volume. Okay, so again, Riemann sum, integral notation, or alternatively and more conveniently, just use the shorthand all the way through. Okay. Keeping in mind that this is just a shorthand for that. Okay. All right. How do you compute a triple integral? All we know so far about triple integrals is that triple integrals are Riemann sums. We know that Riemann sums are inconvenient to compute, a bunch of algebra at best. At worst, it might be intractable. So, is there another way to compute a triple integral? And the answer is yeah, you can compute a triple integral with a nested integral, like I've done here. And it's, again, sort of symbolically, you might say, in terms of what we write down. It looks like exactly what you would expect. It is, you'll notice, a z integral of a y integral of an x integral, with the integrand being the same as the original integrand. Integrands don't change when you switch from triple integral to nested integral. Now, why is this true? Well, I'm going to not be able to give you a very satisfying answer to why this is true. I would like to say for reasons that are analogous to why they were true for double integrals. Now, what point of view did I give you on this for double integrals? Well, for double integrals, there was no z slicing, right? And this was an integral dA. And the argument I made was that, well, I can think of each of these as being a computation of volume. And I argued, well, if you can compute volume in both of these ways, then it would stand to reason that these two things should equal to each other. Well, now, here that we are back in triple integral world, these things are not equal to a three-dimensional volume. They're equal to, well, this thing that we already got through complaining about that we don't have any actual intuition for because we are mere three-dimensional mathematicians, right? So this intuition, or this sanity check, this point of view, this motivation for why it is that triple integrals should equal to nested integrals, we don't have enough dimensions of intuition to be able to see how that motivation works, right? But algebraically, it's the same, right? So now that algebra, again, is beyond what we're going to talk about in Math 212. So let me just appeal to your sense of pattern that this ought to be true, and I claim that it also is true. But it is pretty hard to see from this context. Okay. By the way, notice, again, you can do the differentials in, I'm going to say either order. Right? With double integrals, remember you could do this or that. You have your choices. There's two different ways to do it. Well, here's the thing. Now we have 3. And it's not just this or this. There's all possible different ways that you can order 6 things. Order 3 things. If you think about the number of different ways you can order 3 things, there are 6 different ways that you can order those 3 things. So we can do dx first, or dy, or dz. There's 3 different choices, after which you still have 2 choices of what to do with the last 2. So it's 3 times 2 is 6. So, ... Didn't have enough space to write them all down, but you see the pattern. As with double integrals, the differentials and the corresponding bounds pair inside to outside. Right? Not left to right, inside to outside. So if you switch these, you have to switch those the same way. They have to correspond. Outside goes with outside, second goes with second, inside goes with inside. Okay. Again, that's very important. Okay. Let's do a calculation. So we have some solids occupying the unit cube, and we have mass per unit volume, density, given by a certain formula. Let's compute what is the total mass inside of that cube. Okay, 3-step argument. Step 1, triple integral. Let me do it like this. Triple integral. The total mass is the sum of the little pieces of masses, each of which is the density times the volume. So, triple integral. Step 2. Theorem above says we can compute triple integrals with nested integrals, iterated integrals. Step 3 then is evaluate the iterated integral. Okay, so let's go through this process. You're going to notice very strong analogies to double integrals, so I'm going to go through this fairly quickly. Again, we have to start with the inside. We have to work inside out. I can't do the dz integral first because the dz integrand, the function of z that is the dz integrand, I don't know what it is yet. I haven't evaluated those inside integrals yet. So you unavoidably have to go inside out. Okay, so x, antipartials. Don't forget what's a constant and what's not a constant, right? X is the variable, y and z are constants. So note how their antiderivatives are accordingly reflecting the fact that they are constants. X going from 0 to 1. Plug in those values. Again, I strongly recommend that you indicate on here that it is x into which we're plugging these values of 0 and 1, because otherwise it's really easy to get confused. And then repeat. Right? So here, the y integral. Y is the variable. Z is a constant. Plug in these bounds. Indicate what variable you're plugging them in for. And then finally, the outside integral. That's a truly, no kidding, single variable integral, and y'all know how to do those. It's the same pattern, it's just that one's really familiar looking. Okay, everybody see the process? Okay. Non-rectangular domains. By the way, you might notice the pattern. We're going through the same pattern of we motivated triple integrals, and then we wrote down a definition of triple integrals, and then we talked about nested integrals, and now we're talking about non-rectangular domains. It's the same sequence of ideas that we went through with double integrals, and then we are going to do a bunch of examples as well. So one of the big lessons, recall, about double integrals is that the domain is all you need to draw a picture of in order to figure out the bounds. Right? So you can't, if you're doing a double integral, what you're thinking of as computing volume under some surface, yeah, you could slice the volume, but then you notice that, look, the slices I do on the volume, look, it's all dependent on just, how am I effectively, equivalently, just slicing up the domain. And it's a lot easier just to draw the pictures of the domain. Right? Anything vertical in the graph picture is just telling you about the integrand, not the bounds. So we only have to draw the domain and then slice up one variable at a time, depending on how you ordered your differentials. Look at the range of values of those appropriate variables. And keep track as you go along. So let's do one. Now, this will be our very first triple integral. Here is our first domain that we're going to consider. This is a tetrahedron. These vertices here are all at ones on their corresponding axes, and fourth vertex being the origin there. So it's an easy tetrahedron. And suppose that's our domain for some triple integral. Now, why would we want to consider a triple integral over this domain? I don't know. Maybe we want to compute the mass, and we're doing a triple integral of density. Maybe we're computing the number of flies flying around inside of this netted area, and I know fly and population density, something like that. So let's not worry about what the application is, what the integral represent, or what the integrand represents physically. That's whatever the application is, those corresponding integrand. I just want to talk about the domain and the bounds. So we have a three-dimensional domain. I want to talk about what are the bounds on the corresponding nested integrals. Okay, so we can slice this up kind of however we want. I've made an arbitrary choice here that I want to do the differentials in that order. Again, you have 6 choices. Right? By the way, you might be wondering, which one is the best one? Which way should I slice it? Hard question. Like with double integrals, there's going to be motivations. We're going to try to avoid slicing through corners. We're going to think in terms of what do I want to solve for in terms of what else, that kind of thing. We'll talk about those details later. For the moment, I'm picking one arbitrarily. We're going to do our DZ slicing. I'm going to say first, and then we're going to do X slices of the Z slices, and then et cetera to Y. We'll see what that looks like. Okay, so starting with Z, analogous to double integrals. This is what a Z slice looks like. If I take a slice perpendicular to the Z axis, corresponding to a particular value of Z, that slice is a triangle. Yeah? Okay. Let's think about what the range of values of Z is. Well, these slices, they don't all look the same. They're bigger down lower and they're smaller up higher. All right, but all together, the lowest value of Z, the lowest slice, is we can look at the shape of the tetrahedron. The XY plane is kind of the base face down there. So Z equals 0 is my minimum value of Z. We were given that this top vertex is at 0, 0, 1, where I know Z is equal to 1. So the bounds here are 0 to 1. Whoops, where'd it go? There we go. Z goes from 0 to 1. Everybody on board? Okay, next, having figured out the Z bounds, I'm now going to go on to the X bounds. And now remember, just like with double integrals, let's remind ourselves how double integrals work. With double integrals, you do your slicing in one direction, and then on one of those slices, you look at the range of values of the next variable. So the same thing applies with triple integrals. When I say I want to know the X bounds, I'm not saying that I want to know over the entire solid, I want to know the range of values of X. No. We've already done our Z slicing. We've agreed that Z goes from 0 to 1. I'm now going to focus my attention on that one Z slice, and on that one Z slice, I ask the range of values of X. Okay, so we're not looking for, X goes from 0 to 1. That's not at all what we're interested in. We're only interested in the existing Z slice And it's only on that z slice that I want to know the range of values of x. So we start off, there's our lowest value of x. That's sort of, if you will, the first x slice of our z slice, et cetera, et cetera. There's our last one. All right, so my starting value of x, I have a picture down here. My starting value of x corresponds to that first slice. Not hard to persuade yourself that x is 0 there. Our last value of x, we're going to play the usual game to find that upper bound. That upper bound corresponds to that point. All right, we're going to play the usual game of you associate your bound to a point. Sometimes you get lucky, it's a collection of several points, whatever. Here, in this case, that point. That point is on certain geometric objects. Those geometric objects have certain equations. Solve for the variable you're interested in. Right? Same pattern that we did for double intervals. Now, let's write down what do we know about that point. We've got to be careful here. What do I know about that point? Okay, well, for one thing, I know that that point is on that plane. Now, by the way, you hopefully see here the value of having a really good picture. You're really going to have a good picture because your solid is not just something that you contemplate once. You have to think about what do slices of it look like, and what do slices of the slices look like, and various points that are on certain slices of faces of your solid or on which kinds of surface. Oh my gosh, you really need a picture. Right? Make sure to draw yourself a decent picture. And by the way, I strongly encourage a large picture because however big your picture is, you're going to be doing slices of slices and things are going to start getting close together. So if your picture's too small, it becomes unusable pretty quickly. Give yourself a nice, good picture. Okay, remind, I was a sidetrack. So we're looking for this upper bound value for x. That x bound corresponds to that point. That point, among other things, is on this red plane. That red plane has this equation. Right now, does that allow me to solve for x? Well, not really. I know y is 0, but I need to know what x is at that point. Now, what else do I know about that point? Well, I know that that point is on this plane. That plane, I'll refer you back to chapter 1, has that equation. So I have two equations now. The value of x that I'm looking for corresponds to a point that's on various surfaces that have these equations. So I'm looking for an x that satisfies both of these equations at the same time. And there's a third piece of information I know, and that is that I already know what z is, right? We agreed already that z is the value corresponding to that slice where I'm at. And just, this is a little silly looking, but I like to just write z equals z. And of course that doesn't really mean anything, but this is my little way of reminding myself that I know what z is. Z is given. It's fixed. Or said differently, I'm trying to find this x bound as a function of z. So I get to pretend that z is known. Okay, so with all of this being the case, keeping in mind I'm still trying to find x. Can I solve for x in this trio of equations? And yeah, sure you can. It's a little bit of algebra, but x is, whoops, sorry, pencil. X is, well, let's see, it's 1 minus y minus z, but y is 0. Sorry about that. I can't find my mouse now. There it is. Go away. Y is 0, so x is 1 minus z. Don't need to solve for z. Z is fixed. Or said differently, I want to know how x is a function of z. So there you go. Everybody on board? Now the details of this particular bound calculation are not terribly bad. The algebra was really easy. No tricky curves. The art wasn't that challenging, right? But let's talk about the process, though. I hope everybody sees the process. That we realize that, the way you figure out bounds is you figure out that that bound is associated with a certain point. That point is on certain geometric shapes, surfaces in this case. Those surfaces have certain equations, and then don't forget to solve for what you're interested in. Again, if you were to say that the x bound is x plus y plus z, or x plus y plus z minus 1, or something, right? That doesn't make any sense. Okay, so 1 minus z. Yeah. So x 0 to 1 minus z. Okay, let's do the third bound. So now that we have a range of values picked, z goes from 0 to 1, and now we've agreed that x goes from 0 to 1 minus z. Now what about y? What's the range of values of y? Okay, I emphasize we are not talking about over the entire solid, how y ranges over all of these different values. Not at all what we're interested in. Right? We're looking for how y ranges over the region that the slice that we've already decided to focus on. So we've already decided that we're focused on this z slice. For that z slice, we talked about the range of values of x, and now we fix then a value of x. So we look at this x slice, a slice perpendicular to the x-axis, this x slice of our z slice. That gives me this little yellow line segment, and it's on that yellow line segment that I want to know what's the starting value of y, and what's the ending value of y. We're not interested in the range of values of y over the whole solid, only on the relevant slice. Okay, so have that picture already drawn here. Right, what can I say about that? Our lower bound for y, well, I'm looking at that point, and I could play the usual game and start listing properties, things that I know about that point. I know what x is, I know what z is, but it leaps off the page that that point is on the xz plane. It's on the plane that says y equals 0. So within algebra that includes the equation y equals 0, solve for y is 0. That's a freebie. Right. The upper bound, though, not so free. If I want to know what is y2 corresponding to that point, I have to ask the question, what do I know about that point? And I know 3 things about that point. On the one hand, that point is on that plane that has the equation x plus y plus z equals 1. Another thing I know about that point is it is on that plane, right? It's on my z slice. In other words, I know what z is. And finally, that point is on that slice. In other words, I know what x is. These last 2 observations, that I know z and I know x, these are just recognitions that I've already decided, I've already fixed z and x, and it is for those fixed values of z and x. In other words, on this x slice of this z slice, that I want to know the range of values of y. So there's my algebra solve. Right, we're looking for y. So we solve for y in this equation, and we get y is equal to 1 minus x minus z. Everybody happy? All right. So, as previously agreed, z goes from 0 to 1. X goes from 0 to 1 minus z, and as we just saw, y goes from 0 to 1 minus x minus z. Okay, it's just like double integrals, non-rectangular domains for double integrals. So we did a bunch of this kind of thing yesterday. It was just a two-dimensional version yesterday. This is just a three-dimensional version of, morally the same thing. We draw just the domain because it's easier. And then you start slicing and keeping track of values as you go through the slicing process, outside in on the integrals. Okay, so computationally, same region above. Suppose the density is this. Compute the actual mass. Again, three-step process. We've already agreed. Mass is triple integral of density. Right, Riemann sum. Density per unit volume times volume. Sorry. Mass per unit volume times volume gives you mass. Right? Mass is an accumulating quantity. Triple integrals are computed with iterated integrals. And now comes the computational process. Antiderivatives. Now, you've got to make sure to do your antiderivatives in the right order. Right? Got to do the dy integral first. So we're treating x as a constant. So the antiderivative is just 6xy. You plug in these bounds. Now again, it feels a little bit weird to say that y has a value which is a function. Right, plugging in y equals 1 minus x minus z feels like a weird thing, but keep in mind, for the purposes of this integral, this inside integral, we're looking on an x slice of a z slice. So x and z are fixed, they're constants. So this really, for the purposes of the inside integral, these are constants that we're plugging in for y. Okay. That gives us this integrand, and so now we have a dx integral to work out. Keep in mind, x is the variable. Z, further to the outside, is therefore a constant, so we treat it as a constant in that algebra, right? Because it is a constant for the purposes of that algebra. Again, plug in the values of x as indicated, and then finally we have a single variable integral, third step in the process. It's the same game, except there are no constant variables. We've already gotten rid of the y's and the x's, and this is just a plain old single variable integral. Okay. So make sure to keep in mind what roles are being played by what variables at what stage inside of a triple integral. Right? For the purposes of the inside integral, x is the variable. X is the only variable. We're treating y and z's as constants because we've already fixed those values. We fixed the values of y and z as we were going through the y and z slicing processes. So let me say that a little bit differently. Any variable that is further to the outside in the nested integrals, any variable whose differential is further to the outside, is to be treated as a constant for the inside integral. So for the inside integral, y and z are constants. When we get around to doing the sorry. Get around to doing the dy integral. By the way, let's talk about the x's first. Where are the x's in the dy integral? The x's are gone. There are no x's left. X was a dummy variable for the inside integral. I've already plugged in x to be certain functions of y and z. So anywhere there had been x's, there are now just y's and z's. So the x's have disappeared completely. And for the purposes of this dy integral, there are no x's. Y is the dummy variable. And the variable further to the outside, z, treated as a constant because it is a constant. It became a constant when, as part of the dz slicing process, we took a slice perpendicular to the z-axis, thus making z constant. Okay. All right. So what I have left here, we've got 35 minutes. I've got a bunch of examples. And I think it's good to spend time with a bunch of examples on triple integrals. I admittedly went fast through all this development of what's the definition, what's the intuition, what's a nested integral, what happens with non-rectangular domains, right? Because it's so analogous. It's so analogous to double integrals, right? So I think it makes sense to go through that reasonably quickly. But the various kinds of pictures you have to draw and thinking about your various strategies. You have 6 different ways to slice. What's the best way to slice? These kinds of questions. There's a lot of just kind of getting to know the process that I think is helped dramatically by just doing a bunch of examples. Okay. All right. So next example. We're going to do a triple integral over a ball, the unit ball in R3. Now again, why are we doing a triple integral over the unit ball in R3? Maybe we want to compute the mass inside the ball and we're given density. Maybe I want to compute the number of fish in this region of the ocean, and I know fish population density or concentration or whatever, right? What the application is, whatever. So I want to focus here on how do I take a domain and turn that into bounds on my iterated interval. Okay, arbitrarily, I'm going to use this order to slice. Notice we're doing our dx integral first, then dz, no particular reason, whatever, and then dy. Okay, so starting with dx, let's look at our domain, unit ball in R3, and we ask what's the range of values of x on that unit ball in R3. Here is that unit ball. Let's see, I hope it'll let me, yeah, okay, cool. So here's a unit ball. By the way, you'll notice that I'm looking, if you look at where the x, y, and z axes are drawn, it's as if I'm looking not quite straight overhead, but I don't have the usual shallow angle on it that we normally take. I'm looking at it kind of from above. The reason is that if you take a ball the way we normally think about it, kind of like that, and then you try to draw a cross section like I've drawn here, it's a lot harder to draw, and it's a lot harder to see how the cross section is different from the solid. Whereas if you take a steep angle on it, you can kind of it makes the cross section slice. It's just a little bit more visible, I think. Okay. All right. So here's our ball. This is what our cross sections look like. Perpendicular to the x-axis. And think about, how many different cross sections there are. And the first one is back there. This is a ball of radius 1, so that's where x is -1. Last one is over here. X is +1. Pretty straightforward to see that x bounds are -1 to 1. Yeah? Everybody good? Okay, so x goes from -1 to 1. Okay, now, as usual, we're going to focus our attention now on a particular x slice, an arbitrary x slice. So I'm going to fix that x now is that value. The corresponding slice is this disk. All the rest of the interest that I have, and bounds for y, bounds for z, whichever, I've already forgotten what order we're going in, but all of those bounds are bounds on this x slice. I don't care about this part of the solid over here anymore. This part of the solid is going to be part of our calculation, but it'll be part of our calculation for a different value of x. We're right now considering this value of x. Okay, so on this value of x, I want to know what's the range of values of, let's see here, I'll use green. I missed. Harder to aim this thing than you'd think. Z, range of values of z. Okay, so hard to draw, but on this x slice, what does a z slice look like? Okay, let's So a z-slice, that means a slice perpendicular to the z-axis. So a horizontal slice here. A horizontal slice. How does that slice up this disk? And I claim it's going to be kind of like that. Everybody see the geometry there? We've got our ball. We took a vertical slice perpendicular to the x-axis. Perpendicular to the x-axis. That gave us a vertical disk. And then we're taking horizontal slices of that disk. And that gives us these little green line segments. Here's an artistic observation, by the way. How do I know how to draw? Which way do I orient? Are the slices on this picture, are they like that? Or are they like this? How do I draw them? Well, appeal to your geometric intuition. If you take a vertical slice perpendicular to the x-axis, and then of that x slice you take a z slice, I appeal to your intuition that those corresponding little twigs are parallel to the y-axis. And notice that I drew them as being parallel to the y-axis, as best, reasonably best I could. All right, so that's a tip-off. If you're looking for, guidance on what's the best way to draw what I've got, think about what you're interested in and what it might necessarily have to be parallel to. And if it's in 3 space, actually parallel to something, very useful to draw it as being parallel. Helps a lot for perspective. Okay. Right. Okay, so my lowest slice is going to be down there somewhere. My highest slice is going to be up here somewhere. And what can I say about those slices? Okay, well, so again, look at the picture and ask myself what I know about these slices. And so again, having a good picture is really helpful, but also having good geometric intuition for what these things look like is also really helpful. This class is unavoidably geometric. It's just part of what this course is about. So here's the way to think about it in this case. We have this ball. We've taken this slice. We're looking at this disc cross-section, and I'm asking for where is the highest point on this vertical disc cross-section. I appeal to the notion of symmetry here. I claim that point has to be where y is equal to 0. And it's in the middle, if you will. There's a sort of equal splits on either side of that line, if you will. So y is equal to 0. Of course, we also know what x is. X is whatever the value of x represents, that x slice. And we furthermore know that this point that I'm interested in is on the sphere, where x squared plus y squared plus z squared is equal to 1. Now keep in mind what I'm interested in finding. I'm interested in finding z. Right, we're looking for z bounds here. Let's see, I guess I'll use yellow. I'm looking for the z coordinate. So solve for z. And let's see, we're going to solve for z. We're going to move all this stuff over to the other side. Oh, y is equal to 0. That makes this term go away. And we end up with plus or minus. We'll have to address that in a moment. Plus or minus square root. So let me put a question mark there. The square root of 1 minus x squared. Everybody on board? So what do you think, plus or minus? I mean, keep in mind we're looking for the upper bound here. Do you think that the z-coordinate of this point, the top point on this slice, is that z-coordinate positive or negative? The higher of the two. It's positive. So our geometry tells us that it's the positive square root. Okay, now let's go through this analogous calculation here for that point. You know, the one at the bottom. How are we going to find our lower bound for z? Well, that point, the lowest point, also y equals 0. Still on my same x slice. Again, on the sphere that has this equation. So solving for the coordinate I'm interested in, I'm looking for the z coordinate, whatever that z coordinate is. Still solving for that. Pretty much the exact same algebra. I again get plus or minus. Again, I have to decide which. The only thing that's different is that here, since I'm looking for the lower bound point, clearly the point I'm looking for is negative, so I'm going to take the negative square root here. Everybody happy? All right, so back up to here, and you know, whoops, here we go. So notice, again, it won't let me do that. As we previously discussed, x goes from -1 to 1, and we just got through arguing that for a given value of x, z goes from negative square root 1 minus x squared to positive. Okay. Different geometric details in every example, but the pattern holds. It's always, you find the bounds by going outside in, looking at corresponding slices, thinking about the range of values of that variable on the corresponding slices, and then, you know, moving one step in at a time. All right, so let's just to wrap this up, let's find the inner bounds. So for the y variable, you know, what are the y bounds there? Oh, I forgot I had this picture. Yeah, here's that picture I was trying to draw. Top point gives the upper z bound. Bottom point gives the lower z bound, because those are the first and last. First and last horizontal slices of that slice. Okay, so now moving on to the next step, I look at an arbitrary z slice. So we're going to fix a value of z. We're fixing that value of z on this x slice for which we've already fixed a value of x. So we take an x slice, now we're looking at a z slice of that x slice, and it's on this yellow line segment, this z slice of this x slice, that I ask the question, what's the range of values of y? So I want to look at that point and that point. I want to know what are the y coordinates of those points, and I have a picture for this as well. Here it is. So y1, y2. You may have noticed the pattern, the algebra that goes into the bounds. There's so many symmetries on this picture that the algebra is very practically identical for finding the y1 bound or y2 bound. For both of these, I know z, I know x, and both of these points are on the sphere. So let's see here. I know that x is whatever it is, and I know that z is chosen, and I know that x squared plus y squared plus z squared is 1. I'm interested in solving for y bounds, so I solve for y in these equations. And so y ends up being plus or minus square root of 1 minus x squared minus z squared. Again, you can probably see this coming. The lower bound is the negative one. The upper bound is the positive. How we doing? Is everybody okay? Feel free to ask a question. We're doing pretty well on time here. Okay, so let's do a couple more examples. This next example, this is a weird shape, deliberately weird. Every so often, you end up with weird shapes like this. What we're looking for is the surface that's bounded, the solid that's bounded by these two surfaces here. On the one hand, we have that paraboloid with that equation, and then we have this paraboloid with that equation. We're looking for the solid bounded by those two surfaces. Now again, that term bounded by, you got to be careful with that. I don't mean this kind of, the everything below kind of region, because while the boundary includes both the blue and the green, admittedly, right? This is not bounded. Likewise, this region in here that kind of sort of wraps around on both sides, that, what would you call that? Well, whatever that thing is, that region's not bounded. It just keeps going, it keeps getting bigger and bigger in the upward direction, so not bounded. So we are interested in this region. And it's hard to draw a good picture of these three-dimensional regions that let's see here. In fact, I've drawn a bad picture there. Let me get rid of that. What we're trying to draw is all of this thing, everything that's below the upper paraboloid, but above the lower paraboloid. And the way I've drawn it, it looks like it has a vertex there, and it doesn't. What it has is a lip that goes all the way around. It's like this is a weird shaped little goblet or something, with a heavy glass base in it. You've probably seen this kind of things before, right? So it's got a thick region at the bottom, but this lip goes all the way around. It's just that it's hard for me to draw the part of it. I mean, it's easier to draw that part, but it's harder to draw this part because then it's harder to make it clear that there's a hole, there's kind of an indentation kind of behind this. So it's a hard thing to draw. And this is the best that I can do here under the circumstances. Everybody see what I'm talking about, though? Okay, so let's think about how we're going to slice this up. Again, we have 6 choices. We have 3 choices for which variable to slice first. Now, the very first comment I want to make is, what would be the worst possible choice that I could make for the first slice? And I propose that z slices perpendicular to the z-axis. Really bad choice, because for certain values of z, those slices are annuli. Right? And you might, you can kind of say to yourself, well, look, we start there, we end here, life is good. Except, we've already seen this with double integrals. When something qualitative happens, when the algebra that describes your inside variables is different for some values of z than it is for other values of z, right, then life is not good. So here, we didn't exactly slice through a corner, but we sliced through a point of interest. Something changed. Slicing through at that level. Okay. And by the way, even worse, let's suppose that I were willing to deal with that. Now, looking at our z slice, how do you do x slices or y slices? And either whether you do x slices first or y slices first, you're going to end up hitting these little edges. And this is going to break into a bunch of pieces. This is a highly undesirable. We definitely do not want to do this. So do not, I beg you. Let's see, where's my, yeah, okay, that was, yeah, fine. You do not want to do this, so don't do d whatever, dz. This is a bad idea. Okay, so let's get on with better ideas. Now, there's different ways that you can think about this. Here, let me just stay on this picture momentarily. One thing we could do is say, okay, I'm going to do x slices first, and let's try to draw an x, or let me do y slices first, because I think it'll be easier to draw. Okay, I'm going to try to draw a y slice on this shape. I mean, that's bad, right? But something kind of like that. Right, the y slice is going to be, there's going to be a parabola. That's the y slice of the lower parabola. Then there's going to be a upper parabola. That's the y slice of the upper paraboloid. And then there's going to be this kind of, sort of V-shaped region in between that is that slice. And having drawn that slice, I could then ask, okay, well, what do x slices of that y slice look like? And you can see how this is going to get to be a hard picture. Okay, so let me show you a better way to go about this. The trick I'm about to show you does not always make things easier, but very often does. I think this is a really useful trick. Okay, the trick is to realize that once you've decided on the order that you're going, so in this, let's see, what did I decide here? In this question, I've decided I want to go dx on the outside and then dy. Having decided that I'm going to do dx and dy first. The argument for your consideration is that if I look at the range of values of x and y on the solid, that's the same as the range of values of x and y on the xy shadow of the solid. Right, so I appeal to your geometric intuition that if I start slicing this up, looking for the range of values of x, I'm doing x slices of the solid. Well, if the shadow is going to get sliced up the same way as the solid itself. The only difference between the solid and the shadow is that I've thrown away the z coordinates. That doesn't change any of the x values. It doesn't change any of the y values. So the x and y bounds on the solid are the same as the x and y bounds on the shadow of the solid. And the shadow of the solid is much easier to work with. The shadow of the solid, let's see here, let's go back up to, let me just write down what we know about these two surfaces. That surface was z equals 1 plus x squared plus y squared. This surface was z equals 2x squared plus 2y squared. If I want to know where these intersect, that means I'm looking for values of x and y where the one z value and the other z value are equal to each other. Right? If I want to know where these two surfaces intersect, I need the x's and y's where the two z coordinates are the same. Which means that I want these two things to be equal to each other, from which it's not hard to see that x squared plus y squared is 1. And it's just a lot easier to work on. This is a disk, right? It's a circle, okay, fine. But it's a circle in the xy plane. And the range of values of x and y on a circle in the xy plane is artistically so much easier to deal with than looking at nasty slices of this nasty three-dimensional solid that we're trying to draw with a pencil. Yeah, everybody on board? I'm a big fan. I'm a big believer in this as a when the opportunity permits, to take advantage of this idea. Okay, so on this circle, life is really very good. I'm going to simplify things by just drawing just the XY plane here. Right, this circle that we were just looking at. X squared plus y squared is equal to 1, and it's not hard to see that x goes from -1 to 1, and then for a given value of x, y, look at the corresponding y bounds, y is going to go from negative square root of 1 minus x squared to positive square root of 1 minus x squared. It's a double integral problem, effectively, so y'all have seen this done a bunch of times. And that gives us these bounds here. X goes from -1 to 1. Y from negative to positive square root. So that's the beautiful thing about it. We had this nasty artistic drawing challenge ahead of us, and we kind of just bypassed most of the artistic challenge, turned it into a two-dimensional problem, and we're 2/3 of the way done with the question at this point, and already, yeah.
But isn't the fact that x squared plus y squared is equal to 1 usually for the fact that the circle should have a radius of 1 everywhere?
Yeah, so the circle has a radius of 1.
So then, shouldn't also the y direction have a distance of 1?
Well, no. So keep in mind when you're looking for y bounds, right? You focus your attention on a particular x slice. So we're not interested in what's the range of values of y on the whole solid. We're only interested in what's the range of values of y given that x is already a known fixed value, right? And so we're looking on that x slice, and if x is known, and if you solve for this value of y, it's just not 1. Yeah. Right. Anybody else? Feel free. Okay. So having found the x and y bounds, now we just need to find the z bounds. This is pretty straightforward, I think. So given an x, given a y, and I'm not going to draw what the x slice looks like because I can't. It's too hard. I'm not that good artistically. But the y slice of the x slice, I know is just a vertical line segment sitting up above the xy that we've already decided we're at. We've already fixed x and y. So that's not hard, right? The corresponding values of z, at that point, what is this z? At that point, what is this z? Solve for z in the equations that I already know, right? So solve for z here, solve for z there. They're already solved for. So those are our upper bounds. Excuse me, our lower and upper bounds for z. Let's see, where am I? Yeah. Z. There. Everybody happy? Okay, by the way, this gives us a tip-off for decision. How would I decide, again, between the 6 different choices of different ways that I could slice. The fact that this worked out so well, arguably I should have seen this coming, but looking at the algebra that we were given, what do I want to solve for? If I'm given these 2 bits of algebra, do I want to solve for x? If at all possible, I would prefer to avoid solving for x, please. Likewise, y. Think you know. So whatever I put as the inside differential, that's the variable I'm going to have to solve for. Well, I would love to have to solve for z. Given my choices, right? I'd much rather have to solve for z. So let's put z on the inside. There's an argument right there for putting z on the inside. That already cuts down 4 of the 6 different possible orderings of which way to slice, and ultimately it doesn't matter, in this case, which way you do these 2. Something to keep in mind. Okay, last example I want to show you. Let's see, here it is. This is just another one mostly about how to make decisions about which order to slice. There's also some artistic observations to be made in this example. So we're looking for the region bounded by the following 5 planes. So 5 planes. Z equals 0, that's a plane. Z equals x. Z equals 2 minus x. Y equals 0. Y equals 3 minus z. Okay. So let's recognize that artistically, this is a really nasty challenge. I've got 5 planes, and what you might be thinking of, your first cut at this might be to, okay, I'm going to draw the one plane, and then I'm going to draw another plane, and then I'm going to draw a third plane, and I'm going to draw these planes, and I'm going to look at this mess of planes, and I'm just going to get it. And I think that's a really hard way to go about it. So I want to recognize, I feel that for me, I think that would be a really hard way to try to answer this question. So I am not at all judgmental if you'd be interested in an easier way to do it. Let me show you what I think is the easier way to do it. And this won't always happen. This is an idea that is useful sometimes because it only comes up sometimes, but when the opportunity permits, notice what we have here, the first 3 planes, no y's in any of those first 3 equations. Now, the fact that there's no y's in those equations means that whether or not a point satisfies those equations has nothing to do with whether or not there's what value y is. Nothing to do with the value of y at all. Said differently, you can change y however you want, and it doesn't affect whether the thing is or is not on the surface. Or said differently, these surfaces are all parallel to the y-axis. So that helps a lot. The fact that these are parallel to the y-axis. So here are z equals 0. I've drawn that. Now you'll see I've drawn that in the xz plane as a line, z equals 0. But thinking of it as a surface parallel to the y-axis, I can just take that line and kind of drag it parallel to the y-axis. That gives me that plane. Likewise for these other equations. These other equations, in the xz plane, I can think of them as these 3 lines. But again, everything as far as these 3 equations is concerned, there's no y's, therefore everything's parallel to the y-axis. And so those first 3 equations, I can argue, just give me what I get when I take a triangle, this triangle that we just drew for those 3 equations, and drag it parallel to the y-axis. So that's the first 3 planes.
But how did you do the line that connects all the 3 lines?
I'm sorry? How did I get these 3 lines?
No, not the 3 lines, but the line on top of the 3 lines.
Oh, yeah. Okay, so the 3 lines themselves came from just looking at the given equations, right? And then you got to know where these points are. Yeah, sure. So, a little bit of algebra to figure out where those points are. And then when you take that point and drag parallel to the y-axis, it becomes, Okay. Okay, so we're 3/5 of the way toward a good picture from this one observation. So it's really helpful. Now, having done that, let's look at the remaining 2 equations. We have y equals 0. Y equals 0 is an easy plane. Y equals 0 is just going to take a straight down vertical cut perpendicular to the y-axis, the cross section of which is a triangle like that. And then we have, let's see, what color did I use? Did I use green already? It doesn't matter. Y equals 3 minus z. No x's. Notice this, there's no x's in here. That means this plane is parallel to the x-axis with y plus z equals 3. Parallel to the x-axis, y plus z is equal to 3. Field your geometric intuition, that means it's an angled cut. Now it's parallel to the x-axis, right? But it's an angled cut coming down like that, and that's going to take a sideways slice through that prism. right, like that. And so what I've got then is a solid that looks kind of like that. So, I mean, geometrically, I mean, you got to take this one little bit at a time, making the observation about how, hey, why is it several of these equations have got us most of the way there? But, then it does remain that you have to look at your remaining things and just think, geometrically about how does this intersect that, and you have to be able to see it three-dimensionally and, represent it on the page. Yeah, here we go. Better diagram. So let's see. Are we out of... we are out of time. Okay, so there's one more thing I want to say about this example. Oh, man. Okay, I'm going to go ahead and assign the homework for this section because we're just almost there on finishing this section. And this is the only section we will have finished today, and it wouldn't be a good use of y'all's time for me to give you a full day off from the homework because that would just get piled on to the next day, right? So I think it's good for us to stay on pace. But the last observation I'll make, and I'll make it on tomorrow, but y'all think about it for now, is, again, there's 6 different ways to slice, and most of them are bad. So just think through, looking at a solid like this, which way would be a good way to do your first slice, and which ways would be bad. Which ways would slice through corners and such. Okay, see y'all later. And I have homeworks to return and attendance to take, so if you'll stick around.